Okay, so you have a new job. Your job is as an engineer. You're going to build a ventilator. How many people have ever, well, you've all ventilated with a resuscitation bag on the mannequins, right? So you were a ventilator, were you not? So what did you need to do as you picked up that bag? What was required for you to be able to inflate those lungs? You got to squeeze it. Okay, so you need some sort of power to squeeze a ventilator. Squeeze the bag, right? How much did you squeeze the bag?
Halfway. The tidal volume. Until it makes it rise.
So you need something as a mechanism to understand how fast, right? There's got to be some kind of mechanisms in there. And then you mentioned about the chest rising and falling, so you need some feedback mechanism to be able to know that I've done the right thing. Okay. Pardon me? Isn't it pressurizing the blower? Well, in the case of non-invasive ventilation, the blower is the thing that's generating the pressure. But the thing that's generating the pressure when we squeeze the bag can be something totally different. It's not my style, but is that yours? Is that for your wrist or your hair? No, it'll clash with my attire. Okay, so this all goes back to the equation of motion. Because what we're trying to accomplish is the left side of the equation based upon the right side of the equation is what the patient has. So there's got to be some sort of pressure creation to overcome the compliance and the resistance of the lung. And if you do the math here, volume measured in liters, compliance measured in liters per centimeter of water, resistance times flow, if you multiply resistance, which is centimeters of water over liters per minute, flow being liters per minute, the units come out to be centimeters of water. So it's how much pressure has to be generated to generate gas flow. And again, the compliance component of that is what we would consider to be elastic work. The resistance part of it would be the non-elastic. When we ventilate somebody, or as we're sitting here, better yet, this P vent is 0. Well, we're not on a ventilator, last time I looked. None of you are being ventilated at this point in time. So we're only focusing on the muscle that our diaphragm is creating, how much pressure the diaphragm creates. Mechanically ventilated patients can actually have both. They can have some component where the ventilator generates a pressure, and at the same time, depending upon how that ventilator is set up, we can have it so the patient also has to generate some effort. It's kind of a combination of both. Okay? But the bottom line is that there's got to be a pressure required to overcome the work associated with elastic and non-elastic things being there. Okay. How many people have ever taken a foreign language? Good majority. Excellent. Yeah, you may not remember it. Well, this is a foreign language you're going to learn that you're going to remember, or you're not going to go very far in the balance of the program. Okay. I'm using terminology very, very specifically. And if I correct you when we're talking, I'm correcting you because I want you to use the right terms. Okay? Because this module, a lot of this modules, all has to do with terminology and classification. And we want to all be on the same page related to this. So, when we talk about a spontaneous breath, specifically, it's initiated by the patient, it's ended by the patient. Always, 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 always. If the breath is started by the machine, it no longer becomes a spontaneous breath.
When you say it's ended by the patient, is that because like you have the inspiratory time set appropriately?
If I'm setting an inspiratory time, it's not ended by the patient. Then it's no
clear,
longer
straight away.
spontaneous.
Gotcha, okay.
Okay. But with the spontaneous breath, it has to be started and ended by the patient. Those spontaneous breaths can be supported or unsupported. Supported meaning I give it a boost. So when we talked about non-invasive ventilation, we were talking about those situations where I created a delta, I created a pressure support to augment tidal volume. Right? But that's still a spontaneous breath because the patient's in control of starting and ending it. Okay. There's also something we'll talk about called tube compensation that is a little bit of a modification of this concept of pressure support. And we'll get there eventually. Mechanical breaths are all other ones. Anytime the patient doesn't start and end the breath, we're going to classify that as a mandatory or mechanical breath. Those mandatory or mechanical breaths can be started by the patient. In other words, the patient tells the ventilator, hey, buddy, give me a breath. Or, in the face of apnea, the ventilator can just fire on its own. Okay? So, there needs to be some way that we can all be on the same page with this. And the people who are the worst to follow are the salesmen, because they will tell you anything. It was amazing the stuff that I could say when I was in sales, and people would believe me. It's like, please, hello, McFly. There's an example of one of the modes of ventilation we'll talk about. And it was a salesman's line. And one time a therapist said it to me. I said, think about what you just said. The line was, this mode delivers the breath at the lowest possible pressure. This mode delivers the breath at the lowest possible pressure. What, other ventilators sit around and say, hey, I can ventilate at 20, but I'm going to ventilate at 25? It's like, duh, all ventilators deliver the breath at the lowest possible pressure. It's all based upon compliance and resistance and flow pattern. And what the mode did, was change the flow pattern. Well, yeah, of course you're going to get a lower pressure. Don't be stupid and think that, the ventilator's got this magic thing inside of it that'll be able to do it. Early ventilators could only do one thing. They were either a pressure generator, a flow generator, volume generator. New ventilators, because they're microprocessor, can be anything. I can be a pressure generator, flow generator, volume generator, time generator, just by a software change. So we need to have some way to understand this. So when I say something is flow controlled, you know exactly what I'm talking about. Okay? And that way then we can compare what one manufacturer calls one thing and another manufacturer calls gives the same exact thing a totally different name. But if we're all thinking about the same way of classifying it, it makes sense. The method that is most commonly used is one developed by a guy by the name of Rob Chatburn, who's a therapist out of Rainbow Children's Hospital in Cleveland or Cincinnati. I can't remember now. But this guy's into physics and into this really deeply, and he gets a little bit geeky at times, but he actually wrote a book, which is the reason why I went back and took calculus, because I realized I couldn't understand some aspects of this without having a deeper understanding of mathematics. Very nerdy. Good website that puts a lot of this into English, so that URL will help you out. The mode, when I talk about mode of ventilation, I'm talking about how the ventilator and the patient interact. So when the patient wants a breath, what happens? How does the patient and the ventilator get together to do something? Back when I was in school, there was a text that was called McPherson's respiratory therapy. Actually, it was called respiratory therapy equipment. And there were 3 modes. Today, the 2009 edition of Mosby's which replaced McPherson's, has 54 names. Now, some of those are exactly the same thing, only manufacturer A calls it this and manufacturer B calls it that. But there's all these different names and terms that are out there. These are the five things we're going to classify. We're going to classify how it's turned, what powers it, what makes it work. When you're squeezing that bag, you have to have some energy from someplace, right? You got to eat. So there's your power source. Here we got to have some power source also. We're going to talk about whether it's a positive pressure generator or a negative pressure generator. We know from non-invasive you can do ventilation either way. Positive pressure, negative pressure. There's got to be something that takes that power and converts it into actual energy, actual movement of gas. That's what we're going to call the drive mechanism. Then there has to be something that controls it. What turns it on? What turns it off? What speed does it go in at? What happens during the expiratory phase? All those things have to be controlled. And then finally, there's some output that we're going to see in the form of waveforms for flow, volume, and pressure. And you've seen those on the ventilators, those displays. Let's talk about the power source first. Got to have something to have gas flow. Now, this is not necessarily the power that's controlling the control circuitry. It's not the computer power. We're just talking about what powers the ventilator itself, what causes gas flow to happen. And there's three ways to do it. Electrically, either through AC current or through a battery, DC current. Pneumatically, where typically we use 50 pounds per square inch of gas pressure, or both. Some ventilators can function with just electrical. Some can function with just pneumatics. Some have to have both. Without both, they don't function. So electrically, obviously, is going to have a power switch. That's always the challenge on most ventilators, is to find where the hell the power switch is at, in case you haven't encountered that. That electricity then is going to control what the driving mechanism is. What's making the gas flow move from point A to point B? And that power can power perhaps a motor, some magnets, something called potentiometers, whatever. All kind of stuff out there. And electrical powered ventilators don't require a source gas. And as we get to camp, we'll find that those kids riding around in their wheelchairs, they have a battery-powered ventilator. There's no oxygen source. It generates its own gas flow. It has a turbine, it has something internal to it that creates gas flow to be able to blow the gas into the patient's lungs. Okay? Most home care ventilators are strictly electrically powered. Okay? You don't need a gas source, which is good because in the home that would mean we'd have to have big cylinders and everything else. Something is specifically only pneumatically powered if the entire reason for gas flow is because of a 50 psi source. Usually they'll function down to about 35, 40. So if you lose gas pressure for whatever reason within the hospital, it still can function, but you need to have some pressure there. True pneumatic ones you've already used. The Bird Mark 7. That's a pneumatically powered ventilator. Doesn't have a plug, right? Just plug it in the wall, a 50 psi source, be it air, be it O2, and it'll function. There are some ventilators that are also called fluidic ventilators, and these are rather cool because there's no moving parts. How the hell does gas move if there's no moving parts? It uses what's called fluidic logic, okay? And because there's no moving parts, there's usually no metal parts, so that means they can be used in MRI environments, which is really important because periodically you've got to take a patient on a ventilator down to MRI. And there's only a handful of ventilators that are MRI compatible. So you know this guy, pressure versus magnetism, right? That's how this device works. It uses the pressure that's coming from the 50 psi source, regulates it down to something usable on the part of the patient, because we don't want to put 50 pounds per square inch of pressure into the patient. Call me silly. Okay? This is the concept of fluidic logic. Did you ever, when you're making coffee, you got the coffee pot, you're pouring it in, or you're pouring it into your cup, and it spills, drips. That mechanism whereby the fluid attaches to the coffee pot and drips on, that's called wall attachment theory. That's fluidics. That bit of coffee should never hang there, but it does because of the pressure changes that exist. And that's what fluidic logic utilizes, this wall attachment theory. Okay? And in this example, what you end up having is so long as there is a gas flow coming through this direction, it'll push the gas flow through outlet number 2. So if I set it up so I have a continuous flow moving through C2, it'll continually move from my pressure source outlet 2. Well, that may be exhalation. I don't want gas flow to go to the patient, which would be outlet 1. I only want it through outlet 2. Then I want to turn the breath on, so all of a sudden I create a oxygen or a flow at C1, pushes it the opposite direction, and continues out to the patient. When I want to turn it off, I just open up the C2 spigot again. So I'm using it to go back and forth. Flip-flop. That's what the type of device is called. Okay? So all I'm doing is I'm using pneumatics to control ventilation. And there's some kind of logic that's telling the machine, go from C1 to C2, to C1 to C2. It's just internal logic.
What causes it to switch?
Some kind of timing mechanism internal to it says, stop going from C2, go to C1 to deliver breath to the patient. Then after a certain inspiratory time, it knows it's supposed to flip itself back. Those are all internal logics that are created within it.
So it's time-based?
In this case, it could be time-based. Okay? I could put a volume sensor down there, measure the flow going through, and when a certain volume is delivered, tell it to shut off. There's all kind of ways to end up doing it. The point I'm making with this is that you don't have to have any moving parts to cause a valve to open and close like you do with IPBB. It's all done through pneumatics, through fluidics. This actually is called a flip-flop valve. What a novel name for it. Okay? Okay.
There doesn't have to be a moving part somewhere?
No. It's the most fascinating thing that you see.
That the guy came up with.
Yeah. All right. Most of the ventilators we're going to deal with, in fact, all of them we're going to deal with in the lab, are both electrically and pneumatically. You can't run them without having some source gas to power it and electrical power. Okay? So electrical power is going to not only control the microprocessor, it's also going to control some internal driving mechanisms, and the pneumatic power has to be there also to create gas flow. Whether it's negative or pressure, we've talked about previously. Negative pressure generators are going to create a negative pressure external to the chest wall within a sealed chamber and cause inspiration to occur. Passive exhalation. Positive pressure ventilation, we create the positive pressure to push the gas in. Okay. So we need to have some kind of a mechanism to create this gas flow. And there's multiple ways that different ventilators accomplish this. Some have compressors or blowers, and this is what we've been working with the non-invasive, the Vision, the V60. They're both creating pressure change, pushing gas into the lungs secondary to a blower of some kind. Sometimes the mechanism is a piston. As you can imagine, if I push a piston forward in a fixed space cylinder, I'm going to create a positive pressure there, which will then displace gas into the patient. That piston, and this gets a little bit geeky, could be linear, boom, 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 could be rotary, where there's a wheel that is turning, and onto that is the piston. There actually is a difference between a rotary-driven piston and a linear-driven piston. And the difference is in how that gas flows. Okay? And you'll have to trust me on that one. There could also be a bellows internally. When we get in the lab, I'll pull the back off of my favorite ventilators I have there, the Puritan Bennett MA1. And you could see the internal bellows that are there, just like you would have with on Julia Roberts. For those of you who don't know the joke, if you when you hear the ventilator, if you've ever seen the movie Steel Magnolias, there's a scene in there where she's on a ventilator. It happens to be the same brand, but the sound is just it just becomes in your mind.
Synonymous with still making.
It does. It does. But there's a bellows internal to that. Same bellows like you would have in a fireplace. Same kind of idea. Okay. Most of the ones that we're going to encounter, though, are some kind of a flow-controlled valve. There's something electronically that is opening and closing, whether it's like a shutter on a camera or a pair of scissors-like valves that opens and closes to allow gas flow, or some other mechanism. There's got to be something electrically is causing that flow to be altered. Many of the ventilators have what is called a proportional solenoid. What the hell is that? Solenoid, a solenoid is a mechanical electric, let me rephrase that, electromagnetic type of device that when current is applied, it moves something back and forth. Okay? Your doorbell is a perfect example. When you push your doorbell, an electrical current causes a magnetic field change that causes a plunger to move forward and ding, hit some sort of mechanism to create a tone. It then releases back once the doorbell is no longer pushed. Okay? So that kind of a mechanism is what is used in our ventilators, and I'll explain a little bit more as we go through. So this is all about how do we get gas flow creation. So here's my blower. We've seen this with the V60 and the Vision. Pistons, pretty obvious. I have two valves, two one-way valves. As I pull gas, as this comes down, gas is pulled in. As the piston moves up, gas is pushed out. So it's just a matter of pulling gas in, filling the piston, pushing gas out. Here's a bellows. A lot of anesthesia machines would utilize that one. It's kind of an old picture, but you get the idea. And then this is the proportional solenoid this is the schematic for the 840, but it's present pretty much on some derivation of this on pretty much all ventilators. Two gas sources, oxygen, air. And what this device does is it opens proportionally so that I blend the gas. If I want some specific FiO2, it knows that it has to open the air this much and the O2 this much. It then keeps those valves open for a specific amount of time and then closes them. So it gets a specific FiO2 at a specific flow rate for a specific inspiratory time. Pretty simple concept when you think about it, but a pretty elaborate setup. Okay, so all it's doing is it's opening and closing a valve that's hooked up to an oxygen and an air source to blend them together for a specific FiO2 at a specific flow rate for a specific inspiratory time. So there needs to be some kind of a, okay, this was talking about the drive mechanism. There needs to also be some sort of a control mechanism that tells the ventilator, start this breath, end this breath. Okay. Also needs to know whether or not the breath was delivered. Was I open long enough? Okay. And was it the way that we intended it? So there's two different ways to approach this. I can have an open loop system or a closed loop system. With an open loop, it's pretty much idiot-proof. Okay. Deliver this tidal volume.
Can you email us this slide?
Was the page loaded backwards?
Yeah, I think so.
Okay. Are we okay? Okay. So an open loop is unintelligent. All it's doing is blowing the gas into the patient. There's no feedback present. With a closed loop system, it's intelligent. It's like your cruise control on your car. It's monitoring what speed you're going at and either increases as you come to a hill or decreases as you come down the hill. There's that, because of that feedback mechanism, it can say, did I really deliver that tidal volume I desired? And if not, how can I change it? Okay, so that's a closed loop. That's the more intelligent one. Open loop, dial my tidal volume for 500, gas blows out. Did I really deliver 500 to the patient, or did some go to the atmosphere? I don't know. Did some get lost inside the machine? I don't know. With a closed feedback system, I'm monitoring downstream and seeing if I truly delivered that to the patient. Okay? So there's 6 basic targeting schemes that we could end up having. In set point and dual control, go ahead.
I'm just curious, with the open loop,
Mm-hmm.
if it's that much, I don't know, like mystery as to what's being delivered, how do we use that?
We would use it in situations where that delivery of tidal volume is not critical. So say a home care ventilator where, you know.
Are they simpler to use?
Oh, yeah.
Or
Oh, yeah. As we go down this list, they get more complex. Okay? So open loop are, it's not that they're bad, it's just that the potential for problems to happen because of other factors goes up. Okay. All right, so let me go through these. Yeah, okay, I'll go through them again. With set point and dual, and this is what we call a target, I set up everything. I go ahead and I tell the ventilator, this is what I want. These are basically open loop systems. With servo, there's basically a generalized target that we have, but it's changing as we go. And I know that's kind of nebulous, but I'll explain what I'm talking about as I go through these.
So servo is not just the name of that.
Oh, that's correct. The term servo means basically something where there's a feedback mechanism. So your cruise control is a servo-controlled speed mechanism.
I was just assuming that was.
No, they just happen to steal the name. The term servo actually goes way before the company stole that. Okay. And then there's 3 that Mary are going to talk about where the ventilator changes itself based upon what it sees. So you start having this piece of silicon taken over the function of ventilation. Okay. So let's talk about set point first. With set point, there's a target that I want to have. And this is where the concept of volume orientation or pressure orientation comes into play. I can mechanically ventilate somebody where I'm controlling the volume that's delivered. Every time a breath is delivered, it's delivered at a fixed volume. In that case, as we know, pressure becomes the variable. I can also have a set point to say, no, I want to have a specific pressure delivered. Each and every time that ventilator turns on, delivers a breath, I'm fixing a pressure. Volume flow variable. Okay? Actually, I not only set a pressure, I have to set an inspiratory time also. Okay, but we'll get to the specifics of these as we go along. So a lot of these modes that we'll talk about are set point. Assist control, volume control. Assist control means what? You've heard that term before. If a patient triggers, it delivers a breath. If they don't trigger, it still delivers a breath based upon a backup rate. So assist control, volume control means I'm targeting a volume, and if the patient triggers, bitchin'. If the patient doesn't, bitchin'. I'm covered either way. Either way, we're happy, right? In assist control, volume control, there's a fixed volume which is delivered whether the patient triggers the ventilator on or the patient is apneic. It'll still deliver a fixed volume. We good on that concept?
And the mandatory just means mechanical, right?
The mandatory means that these are mandatory breaths, mechanical breaths. These are not on the part of the patient. Patient may trigger it on, but it's ended by the machine. Always. Every breath. Okay? When I say mandatory, I mean the patient doesn't end it. Possibly not even start it. Assist control, pressure control. Go ahead.
Can you use this when you're weaning the patient off of the ventilator?
No.
No?
This is typically, assist control is typically a mode which is utilized for full support. Okay. We don't really wean patients. We liberate them. Hallelujah. We just take them off.
Thank you.
Go ahead, Stacy first.
I just had a question. You know how you just said every breath is ended by the machine? Is that true in the assist and the mandatory?
Assist control is a mandatory form of ventilation. There are only mandatory breaths, only mechanical breaths. There are no spontaneous breaths. Can I say that again? Listen closely. Write this down. In assist control, there is no spontaneous breaths. Every breath is from the machine. Patient can trigger it, but every breath is ended by the machine. So therefore, they're all mandatory or mechanical breaths. Okay. Or even if the patient's controlled. All machine. In the case of volume control, it's a fixed volume that we're attaining. That's our target. If it's pressure control, it's a fixed pressure and inspiratory time. Go ahead.
When you say you have like a fixed volume or a fixed pressure, like I would think you'd want to just use volume, but if you would use the pressure, is that based on the patient's lung compliance? Like
Aren't they both?
I just can't picture why you wouldn't use just volume. Why would you be like, oh, I want to set the pressure only at that?
Because when I fix volume, she's got a great question. Why would you want to use pressure? Volume is because what do I fix when I fix volume? What other parameter is fixed? Flow. And we're going to find that that's a real problem. Because it's perfectly fine. This is a perfectly wonderful flow rate when the patient comes out of OR and they're snowed. Now they wake up. And that flow rate may be totally inadequate. Okay. So assist control, we good? Okay. I can do SIMV. SIMV, if you remember, is a combination of mandatory breaths and spontaneous breaths. With SIMV, I dictate how many mandatory or mechanical breaths they'll get in a minute's period of time, SIMV of 10. So every 6 seconds, the machine turns on, delivers a mandatory breath. It's synchronized so that it's not trying to deliver a breath while the patient's exhaling. It's kind of rude, right?
So S stands for
Synchronized. Synchronized, intermittent, mandatory ventilation. What the hell? Synchronized, meaning it's synchronized with the patient. Intermittent, meaning it's not continuous. Mandatory, in the sense that it's intermittently mandatory.
It almost seems like an oxymoron.
I know.
Synchronized and mandatory ventilation.
Right.
The book got rid of S. They said you might just see it as IMV.
You might just see it as IMV. This is correct.
It's the same thing.
Well, technically, for our purposes, no, because there truly is a difference between them. But because there really is no ventilator that does only IMV, we can use them synonymously. But I want to make sure we understand that they truly are two different things. So I have a combination of mandatory and spontaneous breaths. I said if I put them on SIMV of 10, every 6 seconds the ventilator gives a mandatory breath. Well, 6 seconds, I deliver that breath. It might only take a second to deliver it. I got 5 extra seconds there. So they can breathe spontaneously during that time. They start the breath, they end the breath. Basically, the system opens a separate valve and lets them breathe spontaneously. When it's time for the next breath, it delivers the next breath in a synchronized fashion.
Whether or not they spontaneously.
Say that again?
Whether or not they spontaneously breathe.
Yeah, you can have somebody on SIMV of 10 and they never breathe spontaneously.
Okay.
That way they're getting only their ventilation, their minute ventilation is dependent on the machine.
Can you breathe 10 and it never triggers?
Can you breathe on SIMV of 10, have 10 mandatory breaths, and have no spontaneous breaths? Yes.
No, the other way around.
No.
If it's
You're
set-
always going to have the 10 mandatory breaths.
So it would decrease to 20 then?
If you took 10 spontaneous breaths, one between every one of the mandatory breaths, yes. Brian.
Does the system reset after a spontaneous breath?
Oh, yes, quiet. Yeah, the systems are quite sophisticated in that if you were to really stand there with a stopwatch, it wouldn't be exactly 6 seconds because it has a little window in there where it says, if you start at 5.8 seconds, I'll go ahead and give you the mandatory breath now. So, those mandatory breaths that they're delivering can be volume-oriented, can be pressure-oriented. Same as we had in assist control. Okay. Finally, you can have a spontaneous mode, a spontaneous type of breath that is supported or unsupported. And that's what pressure support ventilation is. Pressure support ventilation is where the patient breathes spontaneously and their breath that they're taking is augmented, it's boosted.
But only when the patient breathes.
Only when the patient breathes. If they don't breathe, they die.
No pressure is delivered.
Actually, that's not entirely true, but it's strictly a spontaneous mode in the sense that there's no mandatory mechanical ventilator breaths. So those are set points. I'm setting something here. I'm setting the volume or I'm setting the pressure. In the case of pressure support, that means I'm setting a pressure of some value. You can put it at 0, which basically means I don't have any pressure support, or having the patient breathe spontaneously. But with an artificial airway in that can be, hard. So we typically put a little support there. Lost yet? Okay. We're going to pound this into you. Dual breaths are different. And let me find it. At all? How's that possible? All right, well, jot this down. When I'm in a set point with volume, I'm controlling the volume that the patient is getting. Agreed? When I'm in pressure as a set point, I'm controlling the pressure. You really can only control one thing at a time, right? As much as we like to think that we can multitask, you really can't. At least the ventilator can't. It's pretty stupid.
All right, can you repeat what I have, set point of volume?
I fix a volume and I fix a flow, and pressure becomes the variable, right? In pressure control, or in pressure-oriented breath, I fix the pressure, and the flow and volume become variable. Yes? So I can only control one thing at a time. Well, with a dual, what it does is it flips back and forth. Jackie's question was very intuitive. She said, why would you want to have anything other than volume? You're guaranteeing a tidal volume to being delivered. But the downside is that the flow rate is fixed. Okay. And to be honest with you, volume orientation, up until about probably 10 years ago, that's all we did in the adult world. That's all we knew. Babies, we only knew pressure. And of course, the two of them never talked to each other. In fact, I always talk to my friends up at the U, the folks who work in Mott and the folks who work in the main hospital. They have no idea who each other are. Same department. They both have the same departmental manager, but the two departments never talk. It's crazy. So, volume orientation was kind of what we did in the adult ICU 10 years ago. Now, mainly what we're using is this dual concept. Okay, so Jackie said, why don't we use volume all the time? And I said, because we fix the flow rate, and that may be inappropriate for patients during different times of their stay. So what if I said, I want to deliver 700 milliliters? Okay. The ventilator goes and says, I'll make this a pressure-based breath where flow is variable and deliver a certain pressure, and when I'm done, I'm going to take a look and see what tidal volume was delivered. If it wasn't the 700 I desired, I'm going to boost the pressure. So it's a breath behind, but it's basically the best of both worlds. It's a pressure-based breath targeting a volume, or technically there also could be a volume-based breath targeting a pressure, although really the majority of ones we're going to talk about are volume-targeted ventilation. Okay, it's totally different than volume orientation, because it really is a pressure-based breath.
Is it like an IPPB then?
No, it's like pressure control, which we haven't talked about yet. Go ahead, Brian.
When Dusty and I were messing around with that platform.
Oh, now you're screwing up my ventilators. Go ahead.
That plateau pressure, and you turn off that auto flow.
Mm-hmm.
Does the same.
And these are the examples of what we can do. These three are exactly the same concepts. Pressure regulated volume control. Autoflow, VC+. Buy it today. These are dual modes. These are modes where I'm targeting a tidal volume and it's altering a pressure level on its own to get that tidal volume delivered. Okay. These are dual modes. Mandatory breaths. I'm going ahead and saying, please deliver 700. If it's only delivering 650 with a specific pressure, it bumps the pressure up a little bit. Looks on the next breath, sees where I'm at. If not, makes an alteration again. Go ahead.
What happens in the face of high piece pressure? I mean, you're controlling the pressure, but if you do a bigger tidal volume, it increases your pressure.
If it's not getting the desired tidal volume, it will go up on the pressure. Is there a safety mechanism that is built in so that we don't go above a certain spot? Yeah. There's a whole bigger problem with dual I'll talk about later once you get a little bit of a better understanding of it. If someone told you it's the best thing since sliced bread, you would say, what's the downside? And there's a huge downside. If people don't know what they're doing.
Downside to
Dual control. It's making an assumption that is a very, very dangerous assumption. So in the case of PRVC, pressure regulated volume control, it's really not volume control, it's a pressure controlled breath. It's volume targeted. Kind of a bad terminology they use there. That was the one where the salesman said it delivers the breath at the lowest possible pressure. Well, yeah. If it's seeing the volume being excessive, it bumps the pressure down.
So if you have a pneumothorax, you just keep
No,
going,
don't go
going,
there.
and keep the volume you want.
Any ventilator in the face of a pneumothorax is going to be a problem, regardless of how you have it, right? Untreated pneumothoraces don't do well with mechanical ventilation.
But when it's trying to reach a volume, it just keeps increasing pressure until
It just worsens the pneumothorax, yeah. But that is really true on volume-oriented ventilation or on pressure-oriented ventilation. So don't worry about that one. I can do this same thing where I'm targeting a tidal volume on a spontaneous breath by adjusting the pressure support level, up or down. So let's say I have somebody who's totally in a spontaneous mode. They're breathing totally on their own. Ventilator's just there kind of monitoring their volumes and see if they go apneic. I target a tidal volume. I say, you know what, I want to have that support, that boost. Give me a tidal volume of, 5 to 8 milliliters per kilogram of ideal body weight. And so I tell it, target a tidal volume of 400. It will adjust the pressure support level up or down to get a desired tidal volume. So it's a dual mode in the sense that it's looking to see what it did, changing pressure support level to get to where I want. Those are dual control modes. It's looking at something and changing it. Go ahead.
A spontaneous breath then is initiated and ended by the patient, but can be supported with
Pressure.
extra pressure if the ventilator determines that it's too low or too high.
In the case of volume support, yes. If it senses that the patient's tidal volume spontaneously is less than my target, it will alter the level of boost, the level of delta that it's applying to get to that point. And it does it on a breath-by-breath basis. Okay. But those are dual modes. I'm setting a target, and I'm making an alteration to get to that target. Servo, lastly, and we'll just... I'm sorry, guys. Back to the old days. This is just something where the ventilators, and I'm just going to briefly mention this, just something where the ventilator is making changes on its own. It's not even so much that I'm targeting, but it's seeing changes in lung compliance, changes in airway resistance, and making changes in how that gas is delivered. So now we're getting more sophisticated. Where with set point, the ventilator is just following a direction. With dual, it's looking for some feedback and making a change. With this, it's making changes almost instantaneously. It's seeing how the patient is reacting to the breath and making changes based upon that. And don't worry about the names, because we'll talk about them in a later year. Because now we're getting really sophisticated. Or we're getting more sophisticated. Very, actually.
Seems kind of frightening for a completely new machine and
I don't know. You make automobiles that drive themselves.
That's scary too.
seeing some people drive. I don't know that it's. I don't know what's worse. Okay. Mary will talk about the others in the fall. Okay, so the other three groups. Yeah, yeah. We'll go back and visit these again. We'll talk about tube compensation specifically. Nava's really slick. Nava is where we end up putting a nasogastric tube down or oral gastric tube down, whichever, down through the esophagus. And it has some sensors that identify when the diaphragm's contracting. So it triggers the ventilator on based upon diaphragmatic action. Pretty slick. And PAV is definitely putting the ventilator in the driver's seat. PAV. I like PAV. I do. Actually, well, PAV's cool. Okay. So Mary will cover those in the fall. Okay. So let's take a break. You guys need a break. I'm talking too much. Okay. Part of this control system has to be the mechanism by which you interact with the ventilator, you as the operator. So it could be something as simple as just turning a knob, pushing a button, touching a screen, whatever. There's multiple ways to end up doing that. Okay? And you've seen on the Vision and the V60 that there's some kind of a mechanism where you touch it and you slide it or you do whatever to be able to make alterations. And what we do is we end up changing one or more of four different variables. We're either going to alter the flow in some fashion, the speed at which a gas goes in. We're going to alter the volume to get to a targeted volume, change the pressure, or change the time. So every mode of ventilation is a combination of manipulating one or more of those four variables. And then we end up having, this is the servo eye, you can end up turning knobs, you can end up touching something and making a change with the larger rotary knob to be able to make the change, click it. Did I mention that you have to click it to make the change permanent? The other part is the ventilator circuit itself. There's internally some gas moving around inside the machine, and then there's the external one that we have from the outlet to the patient. Internally, we can classify it as either a single circuit or a dual circuit. The vast majority that ventilators we're going to have are single circuit. The gas that's going through the ventilator is the gas that's ultimately delivered to the patient. Technically, we can have a double circuit, where there's gas that is compressed inside, and then it causes another compression of gas to occur. So there's kind of a secondary circuit. And I'll show you the ME1 has a dual circuit. There's a bellows on the inside that it compresses some gas. It then pushes further gas to the patient. So the gas that is in the bellows being compressed isn't the gas that's ultimately delivered to the patient. Screwy. This is the Servo 300, which hopefully you'll never see in your life. But it has, this here is our expiratory valve and our inspiratory valve, and they're basically little scissor valves. So they open and close just like scissors do. This is an example of a double. So this internal power, this compressor, pushes the bellows then delivers the gas to the patient, but the the movement of gas here isn't the part that's actually delivered. It's called a dual circuit or double circuit. And then there's all kind of other stuff that we can add on externally or added internally to be able to have humidified gas at a specific temperature, all kind of alarming mechanisms, so on and so forth. So where we've gone so far? Well, we've got our input power causing something to convert that into some gas flow. There has to be some mechanism by which the ventilator is telling the gas flow to start, stop, go faster, go slower, whatever, to ultimately get to the patient. And next, we'll talk about this afternoon how the breath is delivered and what control variables there are. Okay.